Okay, so homework solutions. I posted some this morning actually for the homework 5, which was those 3 data sets, including the pollen and the stones and string instrument players. And generally, comments, presentations or the write-ups were quite good. Usually there was not anything particularly wrong with anything, but some I scored just a little bit higher. Some, it would be nice to see a little bit more about inference, either talking about p-values or confidence interval for a slope to get it more in the context of statistical significance a little bit. Others doing more of a conclusion in the context to bring it back to the subject area of the problem would be good, but other than that, I think we're quite accurate. A number of students did a little bit more exploration, looking at logs, maybe picking out a couple points that were possibly outside of the pattern, and just did a little bit more and kind of found some interesting things. Right? So the pollen removal, Lily found that if you take the pollen removal versus the log of duration, things end up looking quite good in terms of the linear model. And I thought of doing that. Others looked at, well, instead of cutting at 31, there's a 31 cut in the first problem. Well, cutting at 31, you kind of are taking out 4 points, I think, but there's really kind of 2 that are really kind of sticking out. So it looks like if you kind of didn't cut it there, but cut it a little bit later, it would make a little bit more sense, or you maybe be able to get a model that includes a little bit more. So people tried a few different things. Some just tried log of x, log of y, and so on, or noted things about other points. So a little bit of exploration was great in that a statistical conclusion, some descriptions of R squared. One thing that came up for a few responses was, well, R squared is only 0.3, or R squared is only 0.4, so it's not very high. Well, in some contexts, that it's very hard to predict, that there's not that direct of a response to the, between the x variable and the y variable. So it's much more noisy. But still, biologically or socially, that might be as good as you get, right? And it's still, it might be still important. So you can get R squareds that are quite low. If you have a big data set, you can have an R squared that's 0.05, 0.1, but it can still be statistically significant. That is, the slope is non-zero, and you're sure it's non-zero, and as one variable increases, the other variable definitely seems to be changing, but there's a lot of other variability. So it doesn't necessarily have to be so close to the regression line, but statistical significance can be different than really explaining the entire pattern. So a few comments, I didn't really mark those as wrong. I kind of marked a note that, well, actually, this is not such a small correlation. It might still be meaningful. It's still significant. So that was kind of that's kind of an interpretation issue. Right? In some fields, R squares of 0.2, 0.3 would be quite small. Physical sciences, astronomy, things with millions, where things are kind of more by natural laws. Other things related to size, right? If you get a bunch of variables that are size related and are regressing on them, you might get very high correlations there because they kind of all go together quite well. Right? Upcoming, there's a homework due Friday where there's 3 problems. Choose one of those. Try to investigate a little bit more, maybe some transformations, report about significance in the context of that problem. So because you're only doing one of those, there's more variables involved, so there's a few more natural things to do, but think about expressing the statistical conclusions around in a conclusion context and explore something or other there. And then the project, I've heard from a number of you about project ideas. That's coming up, so it's good to get a data set and get going on that. Today's Wednesday, so there's Thursday and Friday still this week. It'd be great if you figure out what you want to work on for that project. You have it ready, so there's a weekend to do it, and a little time to write something up. If you have questions about that, about getting a data set, or just unsure about how to get started, I'll be in tomorrow and Friday. We'll have office hours, meeting times, and so on. You also can email if you have questions. So what we wanted to do today is look at something like variable selection. Once you get to a large problem and have many variables, which ones should you put in the model? Should you put everything in, or should you pick some of them? And how do you go about some of that? But that process. So variable selection. So this is really also building a model. You can think about developing a model in terms of which variables to put in, how to put them in there. Which variables as X predictors should be in your model. This also could be how to use X. Should it be X, log X? Should you use an indicator for X less than or equal to some cutoff point? Sometimes there's kind of two groups of X's. There's kind of low and high. And instead of using the quantitative value, maybe you would get enough information by just saying there's a low and a high, like an indicator here. Right? A few principles. Right? Simple models are desirable for some reasons. Simpler models they're easier to interpret. Right? They're easier to explain and communicate. And if they have fewer variables in them, then if somebody else wants to use it, they have to do less data collection. Right? If you collect a certain very specific variable that's hard for anybody else to get, then it might be hard for them to use it in different applications. So interpretation is one issue. And communication, understanding it. But simple models in replication or simple, I guess, in replication. So by that, I mean if you go to a new data set outside of yours, and it's kind of a simple model that shows the relationships that's very strong, it's more likely to be there. If you fit a really complex model to a data set, and it has about as many parameters as it does observations, or it's very complex, it's very possible that you'll get a few influential points in that big complex model that will drive some of the parameter estimates. So when you go and use it in a new data set, the special features of your population or your data set that were there aren't necessarily there anymore, or they're not as strong. So a simple model where there's kind of a simple average or simple relationships, those relationships might carry over more readily to the populations, but it's something very delicate and intricate. As you go to new populations, new age groups, new subpopulations, it might not be as strong. And so you can build something very complex that tries to get to high R squared, but the R squared of the next data set might not be as good. The simple models might have more constant, things like that. Right? But often, many variables aren't good. All right, so often we do those, and generally as the sample size gets bigger, you can often use more variables. If you have a very large sample size, almost everything, well, many things can be significant, and you get quite large models to try and predict. Right? Oops. Models can get bigger.
Is that error just supposed to represent increasing?
Increasing, yeah. So big, big N. Yeah. As it gets bigger, you often have you can put more variables in there, or they're going to be significant. Standard errors are going to be smaller. So you often are still in, you don't so anyway. Yeah. Okay. So how do you do this selection, right, of these variables? So you often, develop some type of base model, right? You have your hypotheses, your scientific hypotheses about variables, key confounding ones, things that you would be in this. So usually fit some model to begin with, but you know that there's differences between subgroups. So you usually kind of start with some base model, call that, model 0. And then you're going to look at the other x variables that you have and either add things to it or take it away. And so there's kind of 3 approaches that people have considered. All right, there's kind of forward selection. So in this one, the current model, if it's model T is our current model, then we would find model T, as would be a L for model T plus another x sub j, a new value, right, for all the new variables, one at a time, right? The model with one expert predictor in there. Calculate a criterion value. And if the new model is better in that criterion, move, and it's sufficiently better, model T plus 1 is the criterion. Something smells good. Right. Is sufficiently better. Sufficiently better. Right, then model T plus 1 includes the new variable. Includes the best new variable. If not, if no variable added to the model makes it sufficiently better, then stay with the current model. And after you select a new variable, you would go back to considering adding a new variable. So it would step through the variables, the set of variables that you might have, pick the best one to add, and then go back and try to add one more, and so on. Just keep building up the model until it goes to some place that you don't get any further improvement. Right? What type of criterions might you do for that? Well, if you do r squared, you add a variable, and r squared is always going to get better. Right? But maybe it wouldn't increase. You might say r squared has to go up at least by 0.01. Right? So you don't want to add an extra variable if it's going to make such a tiny improvement. Right? What are some criterion that we might have in this? Criteria that we might look at. Well, r squared adjusted, right, is something that comes out of there that can go down, right? So if you add a variable in and it doesn't reduce the sum of squares very much, the denominators are changing because you have a different number of parameters, and so that can go down. Right? So this would kind of prevent you from keeping adding variables enough, right? Some look at an F statistic for testing whether the new variable should be added. So if it's one variable, that would be a t-test equivalently. But if you had an indicator, groups that say there were 3 groups, and you have to put in 2 indicators, it's an F statistic. F statistics greater than 4 suggests strongly that variable would be a significant predictor. Right? So it avoids putting in ones that, when added to the model, are not significant. Right? There's a couple others that are often used. There's something called Mallow's CP statistic. And then there's a couple things called information criterion that are often used, right? This is a Bayesian, called a Bayesian information criterion. And this one is based on the likelihood value. It's oops, that's not how you spell it. It's somebody else came up with this information criterion. So AIC stands for this particular criterion. And so you could look at these different scoring statistics to see which appears to be better, right? What are a couple of those things? We won't get too much into the technical definitions of these different criterion, but the BIC is related to -2, the log likelihood function. Likelihood. Plus is P times the log of N. So this is related to the sum of squares errors and the goodness of fit of the model to the data, right? And so that's just something that would be used, calculated from the data. And so the better the model fits, the smaller this is going to be, right? So as you add variables, that's going to get smaller. P here is the number of parameters. So as you add variables, P gets big. So as you get a bigger, more complex model, this is going up while the -2 log likelihood is getting smaller, right? So they're going in opposite directions. So BIC, so we want small values of BIC. Right? So if as you add a variable, if it makes the fit a lot better, this is going to go down and this is going to go up somewhat. Right? This log of the sample size in here means that for a big data set, you have to really improve fit. You can't just get a little marginal improvement of fit. You have to do better for a lot of the parameters. The AIC is very similar to that. It's -2, this log likelihood value, the same thing here, plus 2 times, no, P times the log of N. P times the log of 2. P times the log of 2. So it just has a log 2 in there rather than changing with sample size, right? And again, we want small AIC. So as you add a new variable, it's going to make this go down. This is going to go up. If you add one more parameter, it's going to add log 2 on it. If you have, say, 4 groups, and so you have to add 3 parameters, this is going to go up by 3 times log 2. So the fit has to get sufficiently better, otherwise AIC will go up. Right? So, so in the context of the forward selection, you keep adding variables as long as you can make these things go smaller. The Mallow's CP is another statistic. It's if you have a small model and then a bigger model. So one with a few parameters and then one that's bigger. Right. The CP statistic is P plus the number of degrees of freedom in the residuals. That's N. Right. And then there's a sigma hat squared from the This is sometimes called the full model. And we estimate that sigma, the variance, the mean square error there. And I mean, that's the formula. The book has a little more discussion and a little more detail than we would go into. And what this thing is doing is CP combines a measure of bias, in predictions, and variance. As you get a bigger model that has more variables to predict, you get less bias in predictions, is the idea, right? Is that you should be able to get closer to the actual mean function, right, as it gets bigger. Right? You're actually capturing the details of the relationship that are there. However, if you put in a lot of variables, there can be more variability, right? Up to a point, right? If it's really getting variables that are important, then variability should go down. But as you start putting in extra variables that aren't doing anything on top of the ones you already have, then the estimate of mean square error actually can kind of start creeping back up, because you're adding in noise. Instead of dividing by n minus p, you're dividing by n minus p plus 1, n minus p plus 2. So you're dividing by things that are smaller, so mean square error can get bigger. Right? So there's this trade-off. Right? And so we generally look for the small models with the CP statistic being about p. So again, it gives a criterion that does something more complex in regression that allows you to think about which ones you might use. Right. So, forward selection, you can also do backward selection. Right? Backward selection, you start with the big model and then see what you can take out. Right? I'm not going to write down all of the details of, Right. So you put all the variables you have in there and then tell it to take ones out. It takes out the one that helps you the least. Right? The one, if you take it out, the criterion might actually get better. Right? If it's redundant to another variable or just not correlated or not useful given everything else in there, you can take some out. The fits are about the same, R squared's about the same, and all those other criteria can get better. Right? And then at some point you stop, where taking one out would hurt the predictions too much. The other place is stepwise selection, right? Where you can specify a lower model. What's the smallest model you would possibly want to have? Say you have a treatment effect, and you're interested in that treatment effect. Well, you probably put the treatment effect in there. If you have a few other key variables that everybody's going to think is going to be important, age, BMI, gender, you have a handful that think you have to be there. If you're doing something in diabetes and you don't have baseline blood glucose values, people will say, why isn't that in there? Right? So you force it in there, and that's the lower model. And then you have an upper model that would have all the variables you might want. It might have squares. It might have interactions between things. And you kind of give a starting model somewhere in there. And then you allow it either to add variables or take out variables to move in the direction that makes the criteria the best. Right? And depending on how you do things, you can get different results. Right? If you start with a model and try to go up, and you start with the full thing and come down, you don't necessarily end up at the same place. Right? There's kind of a greediness to the forward or backward selection that it only goes in one direction. So once you add something, you can't take it out. Maybe having a couple other variables in there together would be better than having just one. But if you only go in one direction, you might not be able to get there. You might get stuck. The stepwise selection can sometimes get around that. I guess the fourth thing, the fourth way that this would be done is all subsets. Right? So if you had capital P possible predictors, you have 20 variables, right, available to you that you might put into a regression model. Each model could have, the variable could be in or out, right, binary choice, right? So that means there are 2 to the capital P possible models. Right? This would range from, everything out, which means just the intercept and no predictors, to everything in there. Right? And that's not even counting interaction and so on. Right? So there's 20 variables, 2 to the 20 is well over 1 million. So you can search through all possible models, but for bigger problems, while that's possible, at some point it might not be that advantageous. In the end of this, right, we go through and do some of these selections, maybe look at different criteria, see how they compare. You get what comes down to kind of a final model, or maybe a couple candidate final models. Right? At that point, you have to interpret them, right? What's the R squared? Are they statistically significant predictors? Are there any residuals, outliers, influential points, and all that? But so this kind of automatic searching helps you get from a big set of possibilities down to a narrow few that you could actually think about, right? So that's the idea of this. So let's look at an example. And so one of the case studies, in case study 1102, involved antibodies for individuals with tumors, right, where there was a scientific interest in the relationship between the number of tumors in the brain and tumors in the liver. And so the problem said, a chapter 12 problem, it was 12.14 is the problem. It said to take the ratio of these two in the log. That scientifically that there was some interest in that. So we can do that to create our variable, and so that the response variable looks like this. So we want to predict y. What causes changes on the log scale from -4 up to 2 in terms of that ratio? Biologically, it would be interesting to see, probably due to as the cancer metastasized to other parts of the body and creating antibodies in different places. So you might do some preliminary work. You always want to look at the data to see if there's anything obvious. So here's a pairs plot. It's kind of small to see, but a few kind of interesting things come up. Right, in this top row, y is always going to be on the vertical axis, and this is the relationship to days, tumor loss, and weight. Right? There's kind of a, somewhat of a positive relationship to tumor, maybe not too much of a relationship to weight loss, maybe some positive relationship to weight. Right? And days is kind of interesting, right? It's really 9, 10, or 11. It's at 3 points. And still, if you had to draw a line, it would connect there. But it's really kind of at 3 values, so something about that. So maybe there's some hope, right? There's a few things that might be related. Sex is in there as a binary. Is there a difference between males and females? Yes. Right. So that indicator is likely to be very important. You can check at this point, are there any missing data? It turns out there's no missing data in this data set. But in a real biological data set, some of these variables might be missing. Okay, so it would be kind of nice to check that. So let's select some variables. So I'm going to start just with the intercept as my base model. No predictors. Call that mod 0. And then I'm going to do forward selection. There's a step function in R. So it's programmed in to do this for you. Right? And there's a few ways to specify it. So you start at some point, so model 0. You're going to go forward, and there's an option in this step function where you can specify the so-called penalty function. And if k equals 2, so it's 2 times the p times log of 2 is the added on there. That's AIC. Right? And then you put in there the variables that you could put in there. Right? They have to be in your data frame on that. BIC is the same function, but you do the number of observations. There are 34 cases in here. Right? So log of 34 is more than 2. It's in here somewhere, right? Okay, let's stop doing that. All right, that's good. So if you run that, it runs through selection, and it's pretty fast with 34 observations. And this is kind of what it prints out on the screen. Right? The AIC value it starts with is 56, and then it gives you this output, right? So this is where we are now at no change. And then we're going to either add sex, days, weight, tumor, or loss. Each of those is a 1 degree of freedom add, so only one parameter is needed. This is how it changes sum of squares. Sum of squares regression, and this is residual sum of squares. Right? And this is how with the AIC that we're going to get. Right? So AIC was 56. If we add sex indicator, AIC is 45. That's the smallest of all these. Right? Residual sum of squares is smaller. Sum of squares from regression is bigger. That's a change that happens. But so this would say that the best thing to add is sex. Adding tumor or loss doesn't help you in terms of AIC. Those were not related. Right? So then it adds that, and our new current model is a function of sex, the difference of these two groups. Right? And we're at 45. And then we consider adding the other variables. None is where we are right now. If we add days, sum of squares goes up. Sum of squares regression, residual sum of squares goes down to that. And our AIC is 37. If we added any of these other ones, weight, tumor, loss, it wouldn't be as good in terms of AIC. So we add days. That's our current model. We try it again. Any of these other three we would add would not improve the criteria, and we would stop with sex and days as predictors. Right? So this kind of days, since the tumor was taken out, the antibodies are cultured, so the longer it goes, it seems to make more of a difference. Yeah, so that's what you get. I think you can do if you do a summary of that, what do I call that? Let me go back to type it. Now I saved that thing as model going forward AIC. Right? If you do the backward one, let's see what that looks like. So that started forward. Oh, that's the BIC, sorry. That's not backwards, that's forward. The BIC one, it has a different value here. It's still calling it AIC. That wasn't, but it is a different thing. It's the criteria that you get. But anyway, so it's different values here, but it ends up with the same model. Log of 34 is a little bit different than 2. Right? Log of 34 is 3.5. So it's possible we could have had a difference of variables there, but in this small data set we don't. Now I've saved those. If you summarize that, it summarizes the linear regression model. So it saves the model fit there. So you can get the coefficients, their standard errors, p-values, p-values. Both of them are highly significant predictors. Multiple R squared is 0.49, 49% of the variability in that particular Y variable is related to sex and the days that are there. Right, so you selected those variables. It would be worthwhile looking at residuals and transformations, maybe thinking about that a little bit more, but that gets you to a point. If you do it backward, I could have called model 1, that is all of these variables together. And then, the step function, I'm going to start with model 1. I'm going to go backwards and either do AIC or BIC. Both of these, starting with the big model, so let's look at one of these things, what that looks like. This one starts with everything in there, and that's the none. AIC value is 41.59. And then if you take out this, so it's a negative instead of a positive, if you take out one of those three, you would do better. If you take out sex and days, you do not do better. Right? The one that gives the lowest AIC is this one. These two are almost tied. Taking out tumor or loss would seem to be about equal in terms of the model, but this one's slightly, slightly better criterion value to take out. Once you take that one out, you have 4 that you can take out. Now it says take out tumor. Once you take that one out, you're down to this model. And so we were at an AIC at 35.59. If we take out weight, we go to 37.28. There's a little bit of change there, right? These two criterion values are not too much different, right? You might, if weight was part of your scientific hypothesis and what you want to study in a future study, like if this had been a preliminary study, you might consider the model that has weight in there, right? Because if that's going to be important in your future hypotheses, you might want it in there. And it doesn't, it's about the same in terms of this goodness of fit, in terms of this criterion. But if just by going by AIC, you take it out. So sometimes there's things like some important variables have to be in there to make it sense for your hypotheses and so on. Or your future study is going to use weight. So you don't only go by the criterion. If one of these variables was extremely skewed or had a bunch of missing values or funny outliers, even if this automatic selection said it was good to use, you got to take that into account. Maybe it's not so good for coming up with a good hypothesis or test or something. But anyway, that's the same model. That's there. There's a package called Leaps that I had installed on my computer that lets you do all subsets. Right? So that checks all possible subsets of variables. Right? So this had 5 predictors. There's 6 variables here. One is that y one. Right? And so if you install this package and do library, so it's active, you can do help to see it. And there's one command in that package called regression subsets. Right? It's not part of the default part of R. But what this thing will do is you can do forward or backward or different types of searches. But you can look at all possible subsets. 2 to the 6th, 2 to the 5th. There's only 32 models, so that's not so many to compute or think about. And it allows you to force some things to be in the model. Like if your hypothesis, if there had been a treatment variable and it has to be in there, then you force it in and it never takes it out. If there's some things that are, if you have this big data set and some things are not going to be in there, like you wanted to not include some variable in your data set or had a few but didn't want, I don't know, you could always make a different data set that didn't have those, but so there might be a context for that. And then it gives you, so the number of best by size is 2. So it will give you some indication in this chart of the best models with either 1 predictor, 2 predictors, 3 predictors, up to 5 predictors. Right? So the first 2 lines here, there's 1 predictor. And the best predictor is sex. That was that huge difference in groups, right? If you didn't use that as your first predictor, the second best single predictor was days. Right? Then this line says, what are the best models with 2 variables? Right? Days and sex. If you didn't use sex, days and weight. Right? And then the best with 3 had days, sex, and weight, right? We were kind of getting that from the automatic selection, right? And this is all 5 together. So these little stars in there make you some indication of which models are best over all these, right? Now, if you say I want to use 3 variables, right, then all the ones with 3 variables are, well, they might have different parameters, because if there had been, say, raised ethnic groups in this, that might be several variables, several predictors. So the degrees of freedom might be a little bit different, but in this case, they're just binary or quantitative. So all the values with 3 that have that same penalty. So really, it doesn't matter whether you do log likelihood or R squared, all of those for a linear regression capture that sum of squares error in there. Right? But there's, right. So I call this just a temporary thing. Is that in my, yeah, attempt is, I had saved it there. So I'm just saving the output there. The summary gives you some of this information. Right? There's actually extra things that are attached on that object, right? So R, for a lot of commands, does that. You run a command and it looks like you just have a little bit of information. But really, there's a lot of stuff saved in a list. And you could extract things like residuals and fitted values and that extra stuff that's there. One thing, so a summary of temp is this. Let me run that. The which is telling you which models are used. So which model would be used with one predictor? Is the variable in there or not? So you need an intercept, and then the sex variable is in there. Right? Or the second best one is intercepted days true, and those other variables. So it tells you about which variables are in there. Something else that's in there is R squared. So there's an R squared for all those different models that it lists. There's an adjusted R squared. There's a CP statistic for all those that are in there. And there's this BIC value. So I might just I put these together in this little data frame. So here's my models with 1 variable, or 2 variables, or 3 variables, or 4 or 5. So for instance, this is intercept sex, this one intercepted days, this one has these 3 variables, these 2 variables in there, plus an intercept. And for these, here's the R squared, adjusted R squared, CP, and BIC. Where did our automatic selection things settle down, right? Forward or backward? Right? They ended up here. Right? This model that had the days and sex in there. It has the lowest BIC. That's good. CP was 1.4. Then there's 2 predictors. I guess P would be 3 coefficients. So it's a little bit less than that, right? But it's kind of the same thing. If we have some of these smaller models, right, with just 1 predictor, CP is a lot bigger than 2, right? So that's not good. And if we go on further, the models are getting bigger and bigger and bigger, right? But CP is, well, it's kind of drifting up, actually. So you kind of look at the CP, where does it get kind of low for a small number of predictors? That's kind of where you would want to go for that one. Lowest BIC, if you just look at prediction, R squared, you add 2 variables. Here you had 0.49. The highest you get with all the variables is 0.51. Right? So you get almost all your R squared by just these 2. Right? So they're kind of consistent. Adjusted R squared, right, it can go down as you add variables that don't improve fit, but cost you degrees of freedom. Not good, right? So, like one of these 2 probably would get the highest, this R squared. Right? So anyway, that, or maybe the one with weight if you wanted a more expansive model or other things would probably be done. But any questions about it? You can do it kind of fast. There's many different criteria, but you're looking at, you get R squared, you get these other measurements, and if you just chose the biggest for R squared, there's going to be a bunch of variables in there that don't necessarily help that much. And so if you go to another data set, there could be something that doesn't work out quite as well. The other thing you get with many variables is you get multicollinearity, right? So that's a whole nother topic, right? A concern with many variables, many predictors, is multicollinearity. That many of our x's highly correlated. The problem, so when does this happen, right? So say you had, you're taking dual measurements on some type of energy use, right? And so you have buildings, and you have measurements of energy use, and you have two ways of measuring the energy use. You have kind of like two monitoring systems, one outside the building as energy is coming in, and one inside for some things, right? And these things have a correlation of 0.99 with each other. Right? If you put them both into the model, right, is you can change the coefficient on one of them and do a compensating change on the other coefficient and basically get the same fit, right? And you could do that kind of arbitrarily. You can multiply one coefficient by 10 and adjust the other one drastically. You can make one negative and one positive, and so there's no real way to determine what the real relationship is, right? All linear least squares cares about is predicting y. So it will arbitrarily trade off one versus the other to make a small improvement, right? And if there's almost no difference in those, it's not going to give you something that's specific to your context, right? So it's better to pick one of those, or maybe average them in psychological things, education things, where there's the concept you're measuring is very difficult, and you might ask 10 questions about it, and then score them together. Right? So instead of having 10 variables that are kind of correlated together and maybe trade off in complex ways, doing an average or a rating scale to get one variable to represent the same thing might avoid this, right? So if this is done, so the standard errors on the regression coefficients can be large, and the coefficient estimates can be unstable. So if you change one point by a little bit, the coefficient can drastically swing. Might go from positive to negative, or double or triple or quadruple in size, and there's no sense in which that represents reality in some way. Right? But it's just a kind of an artifact of how we're doing this, and multiple variables in one space, and so on. So it's best to avoid that. Right? And so picking some of these that have really a lot of predictors in there runs that risk of more collinearity and without any real gain. So the next problem in the book said use this same data set, but consider also having a treatment indicator, a time indicator, and possibly interactions. Right? Right, so you could go through and look at the things in detail, but we can kind of automate it with this step function. Right? So a way you can do a help with this step function. So if you type like that. If you help step, let me move this thing over here in preparation. It's a help function for step. Object, we've done directions, backwards and forwards. You can tell it to do both, so it could add or drop variables. You can change that k value to be a different penalty. Log of the sample size for BIC. You can give a scope. Scope is a list of things, of different models you might consider. So I'm going to start with my current good model here that uses a smaller set of predictors. I kind of start with something that I understand, a smaller set perhaps. Right? And my scope, my lower formula is going to be y as a function of sex. Maybe that's related to my hypothesis. I don't have any, it's such a big effect, I have no problem requiring that to be in there. Right? But my upper formula is going to be all the variables, but possibly squared, and this would also get, well, this will get interactions at least. Right? In there. And I'm allowed to go both and use AIC. So this thing, when I do this, ends up selecting sex, time, treatment, and then tumor and loss also get in there. And then an interaction between sex and time and treatment and tumor show up in there. So let's run that, see what the output looks like. Fast for 34. Each time it does this, it has to, okay, it's going to consider, at this point, sex is in there, but there's no interaction. Well, I'm starting with day and sex. So it looks like it's doing one positive variable, and then once these things are in there, it checks for an interaction. Days and sex was not, because it tried to just add a variable. But anyway, then at some point it tried to add an interaction and say, oh, it does like that interaction. And then once that model's in there, it adds treatment. It considers taking out sex and time, so some of these are added, some are taken away. And so on, until it gets down to this point of having this particular model. And this thing is saved, so you can see the output of that. So if I run that, here's the regression output. Oh, it's maybe we need to bleed a little bit more to run all. I don't know why it's giving me that exactly, but most of these coefficients, well, the number of coefficients are significant. For some reason, it has decided it likes this interaction, treatments versus tumor. It says it's not statistically significant. So in the test, the estimate's almost zero, standard. But that AIC criterion seems to have kept it in there. Right? AIC is not as big of a penalty, right? P times log of 2, right? You just have to change the log likelihood by this log of 2, and then it goes down. So it's not as big of a penalty for adding variables. So it's not as big of a hurdle to get over. So it does include this one in there. And other things were significant. Tumor and treatment was significant, but tumor was not. You wouldn't really take out tumor with that one's in there because it's in the interaction. But in any case, why is that one in there? If you look at the BIC criterion with this log of 34, it suggests a smaller model, right? Sex, time, treatment, and then that interaction. It does not include tumor loss or that interaction. So I ran that. The summary of this one, grab that there, right, is. And those things are all statistically significant. R squared is 0.83. The previous one had R squared 0.86. So adding those extra variables only increased a little bit. So you get these two models, kind of a reasonable range of things. Right? At this point, for both of them, you might want to look at residual plot, look at are there influential observations, any particular outliers. you might consider, do you want one of these variables, something in between? And so you've kind of learned something. You've kind of learned about the range of things that would be reasonable for prediction. Right? And there's generally not one particular answer. Right? There's not, we're just trying to fit models that predict the data without overfitting too much and throwing everything at it. Some studies get one data set for fitting a model and then leave some data out to try to validate it. Right? Does it predict well in the new data set? Sometimes those things are called cross-validation. Training, a training data set and then a test data set, those type of things get done in addition to this. But that would be some suggestion of one of these two models or something in between as kind of a reasonable thing. And it's got interactions. It's pretty quick to do that. But any questions about? I looked also at this Swiss data set. Right? The Swiss data set had Swiss municipalities. These were the provinces and a number of things, number of variables there. And looking at I won't look at all, the pairwise plots of some of these things, if that will work. I know that's kind of small, but if you wanted to predict fertility, there's some of these things that are kind of going up, kind of going down. The Catholic kind of has a low and a high with some in the middle. So in this type of data set, if you wanted to you go through each variable, there's some that seems to have an outlier, like agriculture had kind of an outlier, and so on. This regression subsets, you can do it in a couple of ways. In the end, it comes up with education ends up being the first model. When I fit that, using the BIC or the CP statistic, it looked like a model that had, I took out the intercept column to make it fit, but the agriculture, education, Catholic percentage, and infant mortality, those four together were good predictors of the infant mortality. And it had the lowest BIC, a CP that's pretty small. So this would have 1, 2, 3, 4, like 5 coefficients, and CP's right at 5. That looks really good. The model, if I save that and look at the intercepts, these are significant predictors. 1, 2, 3, 4. Where's? Oh, I think I forgot to put agriculture in there, so that's not quite that model, but sorry about that. So that will change things a little bit. I looked at, are there any influential points in here? And so I saved the influence values, these HIs, and looked at some rows. And these couple showed up as HI values that were a little bit higher. Right? The kind of cutoff for some type of concern is about 0.17. So it's really this Geneva in there that stands out as possibly influential in this multivariate regression. Maybe it's a little hard to see. So where is Geneva? Right. Here are the values for Geneva. Right. Here are summaries of these values, these variables across the data set. Right. Geneva, fertility 35 is the lowest. Agriculture 1.2 is the lowest. Examination is the highest. Education is the highest. Catholic 42 is one of these middle ones. Right? So it's kind of extreme on all these, a bunch of X's. You might have seen that because it's so extreme, and it's also capital area, so maybe it's different. So it looks influential. Right? But what happens if you remove it? So you can update the model and change the data set, right? This is the data set is not that, we're not going to use the row where it's, in this case, the names are stuck in the row names of the data set. And this is the fit that's there. And if you compare this to the other one, there's not a whole lot of change. Right? That the individual coefficients don't change, the significance doesn't change all that much. It does, in a decimal place here or there. Right? And the R squared overall, 0.59, didn't really change that much. Well, I guess it went from 0.66 down to 0.59, so it did drop some, but the other things, kind of the substantive model and the prediction for the others, didn't change drastically. So it is unusual in terms of X values. So it could potentially have high influence. But I guess I would be inclined to keep that in there, right? To see if it's, and try to have a model for all the data. It would seem to make sense. It does not seem particularly sensitive. But because it is the capital and kind of special and extreme and all those things, if it had swung things quite a bit on some of those variables, you might have reasonably excluded it. The residual plot is not too bad. This is Geneva over here, kind of sticking out. But the rest of the residual plot is so forth. Great. Okay, well, if I haven't heard from you about projects and you're thinking about that over the next couple of days, that would be great. Make sure you have something to work on. All right. See you on Friday.
Okay. I just like couldn't remember where Okay. Okay.
Good. Thank you. Yep. Have a good day. You too. Yeah. Yeah, that's pretty extreme.
Yeah. And so,
Right, so there's some of the weekly sales that are actually negative or zero. So taking the log makes those, you get a log of a value or a log of zero. So you could take the log of that and then do a regression on the log scale. And it's going to mean that some of the departments that are very small or have zeros or negatives for some reason don't get included in the plan. Yeah.
and so the warning message, so.
Right. Yes. Right. Yeah. So some of them are negative. I mean, some of the departments are small, so they might not have sales in a particular week, or maybe they don't exist at some stores. Some of them were negative. Kind of, maybe they're very small, and they've kind of done some adjustment to inventory or something. So kind of a bookkeeping, they're called negative. Doesn't make any sense to have negative sales, but or maybe people return things and they have to pay them back. So but I think that's fine. I think it should still work if you take the logs. Yeah. Yep.